Okay, good morning, students. So let us start with the today's class. So today, that is semiconductor electronics. We are discussing some questions because in the last class, solar cell and LEDs, its importance we have completed, right? Okay, so we will discuss some questions today on the semiconductor electronics. Tomorrow we will start with the wave optics, right? Okay, so you can see the questions. If you know the answers in the chat box, you can tell me. So see the first question. In semiconductors at room temperature, the valence band is partially empty and the conduction band is partially filled. The valence band is completely filled and the conduction band is partially filled. The valence band is completely filled and the conduction band is completely empty. Yes, which option is right? Option A, B, C, D. Yes. So here what happens in case of the that is semiconductors. Here the conduction band is almost empty and the valence band will be filled, students. Okay, so the valence band will be filled and the conduction band will be empty. So Hagade, which option we can choose? Option A, what it is saying, the valence band is partially empty and conduction band is partially filled. No. Option B, the valence band is completely filled and the conduction band is partially filled. No. So we can go for option D, that is the conduction band is completely empty. And here what happens, the valence band is also completely filled. So we can go for option C and D both. Yes, so we can go for option C and D both. Go for the next question. In the insulators, the valence band is partially filled with electrons. The conduction band is partially filled with electrons. The conduction band is partially filled with electrons and the valence band is empty. And the conduction band is empty and the valence band is filled with electrons. What happens in case of the insulators? Yes. So this is option D, that is the valence band is empty. Sorry, the conduction band is empty and the valence band is filled with electrons. So insulator semiconductors same at room temperature. But when you increase the temperature, havaga valence band in the conduction band ge electrons will go in case of the semiconductors, but insulators alli move agalla. Yes. So in the introduction part, we have discussed here, see students. So what I told you, that is here, if you consider this as the conduction band and this as the valence band. So the valence band is filled in case of both insulators and the semiconductors. But in case of the semiconductors, what happens? Whatever the electrons are there, it will go to the conduction band in case of the semiconductors when you increase the temperature. But in case of insulators, this is not possible. In case of the electron will be there. This band itself, if you increase the temperature, it will not go to the conduction band. So we'll go for the next question. Example for the element semiconductor is silicon, gallium arsenic, anthracene, poly. This is the example for the element semiconductor. Sorry, I did not see. Yes. It was mute. Sorry, I did not see that. So question number 6 we were discussing. Question number 5 is clear, Ala? Yes, question number 5 is clear. Okay, question number 6 I was telling you. No.
No, ma'am, we can't hear you.
Now. Then
No,
from
yes,
beginning
ma'am.
from beginning you did not hear anything.
Ma'am, from 5th question.
5th question only. No, okay, right.
Yes,
Sorry.
ma'am.
Yes. So 5th question, what we were discussing in N type of semiconductor, the electron concentration is equal to. So here what happens in case of the N type of semiconductors? So first we are adding, that is tetravalent silicon will be there. So our germanium will be there. For that we are adding pentavalent. So when we add the pentavalent, here one electron is free. So as one electron is free, here what happens? This is giving me the N type of semiconductor. So what they are asking here, in 5th question, in N type of semiconductor, the electron concentration. So in free electron ide, idu conductivity help ಮಾಡುತ್ತೆ. This will help us for the conductivity. So in that case, here how many electrons are there? It depends on which. It depends on what? It depends on the number of donor atoms. That is option A is the right answer for the 5th question. Next is the 6th question. Which of the following statement is not true? So in the given 5, that is 4 options, see, not true they are asking. So if you see 4th option, a PN junction can act as a semiconductor diode. Yes, this is a true statement. So PN junction is nothing but what? It is a semiconductor diode. It is true. But they are asking which is not true. So not true in the sense you can go for option C. See here, the majority charge carriers in N-type semiconductors are holes. It is a wrong statement. Why? Because in case of N-type of semiconductors, that is, the electrons will be more. The electrons will be more, not the holes. Not the holes. Okay. So this is regarding the 6th question. So 6th question, option C is the right answer. So 5th is completed, 6th is completed. Go for the 7th question. So see the 7th question, what they are asking. Try to answer. So in the 7th question, they are saying that in N type of semiconductor, the Fermi energy lies. Yes. So in case of the N type of semiconductors, option C, the forbidden energy gap nearer to the conduction band. In the forbidden energy gap nearer to the valence band, it is in the middle of the forbidden gap or outside of the forbidden energy gap. So in case of the N type of semiconductor, here what happens? The forbidden energy gap is nearer to the conduction band. That is option A is the right answer. Okay. So question number 7, option A is the right answer. In N and P type of silicon can be obtained by doping pure silicons respectively with. Yes, N and P type of semiconductor. As you know that the N type semiconductor, you are getting it by doing the pentavalent to that doping. And the P type, you are getting it by adding the trivalent, Yes. So in the given examples, see pentavalent and trivalent combination. So in case of the pentavalent, see, I don't know you remember or no, nitrogen will come, phosphorus will come, arsenic will come, antimony will come, and bismuth will be there. These are the pentavalent. So see which all combination we have. Arsenic they have given, phosphorus they have given, indium is there, aluminium is there. So see here option D, indium and boron both are the trivalent. Both are trivalent. Again indium and aluminium, these are also trivalent. Phosphorus and indium, arsenic and phosphorus, these are pentavalent combination. So here phosphorus is the pentavalent and the indium is the trivalent. Yes. So option C is the right answer. So for N type, phosphorus we do, that is pentavalent, and for P type, indium we do, which is a trivalent. Okay, we can go for the question number 9. The element that can be used as a acceptor impurity to dope silicon is. Yes. The element that can be used as a acceptor. So here the options are, that is antimony, arsenic, boron and the phosphorus. So if you see antimony, that is arsenic, and the phosphorus, these three comes under that is pentavalent. So only boron is a trivalent. So boron is trivalent in the sense it is a acceptor. Actually, because when you do the doping with the silicon, here trivalent means 3 bonding will be done. Here one empty place will be there, vacant place will be there. So therefore it is called as what? Acceptor. Therefore it is called as what? Acceptor. So therefore the element that can be used as a impurities to dope the silicon is called nothing but it is a boron. Option C, all three are pentavalent. Here I have written C, pentavalent examples: nitrogen, phosphorus, arsenic, antimony and the bismuth. Go for the question number 10. Among the following, the wrong statement in the case of the semiconductor is. Among the following, which is a wrong statement? Yes, check. Yes, among the following, the wrong statement. Resistivity is in between that of conductor and the insulator. It is actually a right statement. Temperature coefficient of resistance is negative. Doping increases conductivity. This is also a right statement. At absolute zero temperature, it behaves like a conductor. This is the wrong statement. So question number 10, the wrong statement is option D. That is for the semiconductor, at room temperature, it is not a conductor. It is behaving as a insulator. It is behaving as a insulator. Okay. So question number 10, option D. Yes, till 10th question, any doubt is there? Anybody is having any doubt till 10th question? If you want me to repeat any question, you can ask. Okay. Hope so you don't have any doubt. Going for the question number 11 here, students. Band gap in insulator is of the order of. Yes, band gap in insulators is of the order of 6 electron volt, 0.6 electron volt, minus 6 electron volt, 0 electron volt. So in case of the insulator, the band gap, we can consider it as, it is 6 volt, 6 electron volt. Okay, it is 6 electron volt. And for a semiconductor, it will be less than that. So band gap for the insulator, it is 6 electron volt. Option A is the right answer. Going for question number 12, the p-type semiconductor conduction is due to greater number of holes and less number of electrons, only holes, greater number of electrons and less number of holes. So it is option A. Okay. So p-type ಅಲ್ಲಿ ಏನಾಗುತ್ತೆ ಅಂತಂದ್ರೆ holes ಜಾಸ್ತಿ ಇರುತ್ತೆ, electrons ಕಡಿಮೆ ಇರುತ್ತೆ. So here it is conduction is due to both. We cannot say that it is only due to holes. So it is more due to holes, but a little will be there due to electrons also. Option A is the right answer. Question number 13. So similar for the N type of semiconductors it is. So in case of the N type of semiconductor, it is due to, otherwise if you want the exact answer, we can go for option B better. Because some teachers in the evaluation, they prefer the P type of semiconductor, we choose it as only holes. And for N type of semiconductor, go for electrons, only the electrons. Option B is the right answer. Yes, next question. With increase in temperature in an intrinsic semiconductor, the ratio of conduction electrons and holes is. Yes. With increase in the temperature in an intrinsic semiconductor, with increase in the temperature in case of intrinsic semiconductor, ratio of conduction electrons and holes is, actually in case of the that is intrinsic semiconductor, it is 1:1. Okay, it is 1:1, because in extrinsic semiconductor, number of holes and the number of electrons will be different. Number of holes and number of electrons will be different. Okay. Yes, so it is option for question number 14. Option A is the right answer. Going for the next question, question number 15. To obtain N-type extrinsic semiconductor, the impurity element to be added to germanium should of valency. So we require N-type of semiconductors. ಹಾಗಾದ್ರೆ impurity element ಎಷ್ಟಿರಬೇಕು ಅಂತ ಕೇಳ್ತಾ ಇದ್ದಾರೆ, valence electrons. Yes, tell me. 2, 5, 4, 3. Yes, it is option A. To obtain N type of semiconductor, see here, to obtain the N type semiconductor, N type means what? It is having more number of electrons. So N type ಗೆ pentavalent ನೀವು add ಮಾಡಿದಾಗ, so the valence electrons must be 5. So pentavalent ಅನ್ನ ನಾವು add ಮಾಡಿದಾಗ we get the, that is N type of semiconductor. To get the P type of semiconductor, we need to add the trivalent. Okay, we need to add the trivalent to get the P type. So here the question number 17, the majority carriers in a P-type semiconductor are electrons, holes, both, none. Yes. Yes. So next question we are going. So the majority charge carriers in P-type will be, yes, it is holes. Option B is the right answer. Question number 18. On increasing reverse voltage in a PN junction diode, the value of reverse current will, yes. So for the, which one? Reverse current. On increasing the reverse voltage in a PN junction diode, the value of reverse current will gradually increase, first remains constant and then suddenly increase, remains constant, gradually decreases. So on increasing the reverse voltage, here what happens? Gradually the value will be increasing. Option A is the correct answer. Question number 19. In a PN junction diode, in a PN junction, in forward bias behaves like, yes, see, forward bias behaves like, and inductor and conductor amplifier as a switch. Yes, which is the right answer. PN junction forward bias. For forward bias, it acts as what? Whether it is a switch or it is an amplifier. Yes. So it is actually, it is called as, that is integrated circuits anta ಹೇಳ್ತಾರೆ. For the forward bias, that they are only, they are asking forward bias only, no? So we can go for an open switch option. See what they are given, an amplifier. As a switch you select, okay? So go for question number 20. When a PN junction is forward biased, the current across the junction is mainly due to, Yes, in case of the PN junction diode, the current is across PN junction diode. For the forward bias, the current is mainly due to diffusion of the charges, drifting of the charges, both diffusion and drifting of the charges, holes only. So when it is forward bias, it is due to only diffusion. Okay, so it is due to diffusion. Option A is the right answer. So going for question number 23. See what they are asking in the 23 question. When a junction diode is reverse biased, when the junction diode is reverse biased, the current, when a junction diode is reverse biased, the current called drift current is due to, the current called drift current is due to majority charges, majority charge carriers of both N and P sides, minority charge carriers of both N and P sides, holes of both N and P sides, conduction band electrons of N side only. So for the reverse bias condition, they are asking, see. Yes, so what is the answer? You have to revise, students, what we have completed. You have to revise the lesson. This will be a last question because the next question, whatever we have, these questions are not there. It is deleted, right? So just tell me the last question answer. Question number 23. When a junction diode is reverse biased, the current is called drift current. It is due to. It is due to both N and P sides. That is, it is due to holes of both N and P sides. That is the minority, sorry, that is the holes of both N and P side. Option C is the right answer. Yes, option C. Okay, so the remaining part of the questions, it is deleted. So let us not worry about that because it is from the deleted part. Let us see. So here you can see 2-3 marks questions, how they are asking. Distinguish between extrinsic and intrinsic semiconductor, they are asking. Then next, on the basis of the energy band diagram, distinguish between conductors, insulators and semiconductors. Discuss the formation of the N type of the semiconductor, formation of the P type of the semiconductor. So then next, 3 difference between N and P type of semiconductor. Forward bias, reverse bias difference. So you can see many questions are asked based on the differences only. Then we have some of the terms to define: cut-in voltage, breakdown voltage, reverse saturation current. See there. Just go through all the questions. Yes. So you can see that is the main, we have the differences questions, p-type, n-type, intrinsic, extrinsic semiconductor, forward and the reverse bias, and the terms, photodiode, LEDs, and the uses of that. Okay. So these are the important questions on this chapter, students. So next topic, that is the wave optics. That is the last topic which we will start from the tomorrow. Okay. Yes, we will meet in the next class. Thank you. Another 3-4 days, the lesson, the portion will get over, physics. Okay, bye.